And so, when I do Kirchhoff's current law and I add the two currents together, I'm going to say, okay, this one has 416.67, and this is also 416.67, parallel with it, and you add them together and you get 833.33 amps. So that works out. 833 feeding and 833 coming back. And then this one goes this way, 416.67 and 416.67. So you see why they're in parallel, right? You have two paths, 100 amps each. Now you have 800 amps on your spool, roughly. Okay. So if you can solve these, and I would suggest this, then make sure you do not exceed the voltage or current of each winding. That's what you got to do. And how the connection goes, if it's in parallel, then the two currents add together. But if it's in parallel, the voltages are the smaller voltage. So you will always, always, always end up with the total kVA divided by the output voltage will give you your current of the bank. Or not the bank, it's not a bank of transformers, it's one transformer, but of the dual winding connection. Let's put it that way. We're getting to banks of transformers next. Okay, so now we're going to go to this one and say, okay, what about this one? We already calculated 20.83, so it hasn't changed, has it? No. And you got to keep these numbers in your calculator, the 333333, right? It works out better. And then these are 416.67, those haven't changed. Can't even see that. Okay. In series, that's the same current going to, coming back in series.
421.
There you go. So that one works. This one, does this one work? Have 20.83 there, 20.83 there from the jumper. And I'm left with 41.67 because they're in parallel, both currents add together, but it's the lower voltage. Easy, right? What if I connected some things in reverse? Yeah, I gotta maybe show it on the overhead, I think, in this case, because it gives you a couple of examples. You don't want to mix up the 1s and 3s and 2s and 4s. You don't want to have one of the windings backwards, let's say.
Don't cross the streams.
You're fine.
The smaller part.
Okay, so if you're reading ahead, you would have seen this.
Smaller the current, the higher the... Yes. That's the point of a transformer, right? You have crazy high voltage with barely any current, and then you drop it down to lower voltage, but that power has to be turned into something else, perhaps your current goes away.
It's going to be super quiet because Kyle's not. Stand up.
What's wrong with these figures? Here. Page 39. So, looking at the first one, these two are correct. So if you're connecting up the primary, these are correct because, can you not take pictures when I'm standing in front of the class, please?
Oh, sorry.
Yeah. You can always come up or whatever, but yeah. 1 to 4, okay, so that's 1, 2, 3 to 4. So they have the same instantaneous polarity. Let's say 1 is negative when 3 is negative, right? And 2 is positive when 4 is positive, because it will go negative to positive, negative to positive. Easy? Always follow the numbers. Okay, this one here, it's easier to fix, not screw up on this one, because usually you just jumper the two together in series. It's the parallel ones. So if you go 1 to 3, 2 to 4, as long as the 1s and 3s are the same polarity and the 2s and 4s are the same polarity, then you're good. Right? But what happens is the current is causing flux to be established in this core. Without a load connected, it's acting like an inductor. So it's got a huge amount of counter EMF, limiting that current to just magnetizing current. So you're relying on the flux being established in here. If you cancel out any kind of flux effect in the core, it's like you're having zero resistance and just the zero opposition, let's say, and only the wire's resistance will limit the current. So let's see when that happens. If you do this, the flux in the core is negated by the opposite direction of current in the second winding.
No induction?
Yeah.
There's no induction.
No inductive effect means that all you're left with is this path doing this. Back to the source, close to what? 4,800? It might be, I don't know. Let's say it's 20 ohms. I don't know, 20 ohms or something. 4,800 divided by 20 ohms. 240 amps? Okay, that's
Yeah.
kind of, maybe it's not 20 ohms. Say it's 10. I don't know. Depending on the rating of this, yeah. So what it becomes, if this is like, say, 1 ohm, I don't know what the wire's resistance is, but whatever that is, it's going to cause a near short circuit, depending on the resistance of the high voltage winding in this case, and the same with the other one. So let's look at the other one. We go 1 to 2, that's fine, but then we've gone 4 to 3. Right? So we've gone 4 to 3. So this is what you want to avoid, the canceling effect of those currents that will cancel the flux in the core, and now there's no inductive reactance in that core to limit the current. So that's bad. What did I write down? No counter EMF, low R, high I. That's what I put in my notes. No counter EMF, low R, high I, high current. So the top two were correct, the bottom two were incorrect, the C and D. Okay, what about the load side? So that's the line side. We didn't have any load, right? Now let's connect the load. Okay, what about this one? Let's do A and B. We'll just do A and B. This is where you got to put your thinking caps on, as they used to say in elementary school. 1, 2, 3, 4. 1, 2, 3, 4. Looks like the primary is correct, right? So we didn't have the switch closed on the secondary, so we did not know that there was any problem here or anything like that, because we turned on the switch to the transformer and there it is, humming away, but we haven't connected the load on the secondary. Say it feeds a panel, the main breaker in the panel is off, no load, so no problem. Now we connected it this way because we got the apprentice to do it, and he didn't know about the numbering system, and he just thought, hey, you know, I'm gonna copy that transformer and do it the same way. I don't know. So make sure you follow the numbering system. You go 1 to 2, 3 to 4. Is that one correct?
Looks like.
Okay. That looks correct. Yeah. So we're going positive to negative, positive to negative. Yeah, the overall voltage is 240. Boom. We go this one here, positive to negative, positive to negative, in parallel. Looks good. 120 volts is the only output they'll get because they're in parallel sources. So that's like 2 batteries on the secondary doing this. So I've drawn this next to the first one, A. So on A, I've drawn this example here from the two buses. That's like doing this. Make sure I do it right way. And this one would be positive, this one would be negative. We usually use 1s and 2s, but I'm just trying to show you the polarity method. What's each battery worth? There's example A. So the secondary are like a new source that we're going to take a load from. We haven't connected the load. In fact, there's no load connected, even in this case, but we've done the load connections. We've done the connections to the bus that will provide whatever load I connect to. So are we safe to turn the panel on in this case, if it's 240 volts?
Yes.
Yes. As long as it's the right voltage, unless it's the voltage we didn't want. Then we got B. What would that be like? How would I draw that one? My two buses. I want 120.
Parallel.
Yeah. So you put the two sources in parallel, that's like doing this. You don't have to do the little jumper thing over the wire. If there's no node drawn there, that's considered no connection. Right, just so you know that. So 120 and 120 in parallel. What do you think about a battery analogy? Does it work for you? It works for me, I don't know. Does that not work for you?
Drawing a note like that works better, yeah. Disagree with you, but. You disagree? I disagree.
So I got these two wires, and I'm taking this coil and I'm dragging it over here. Now I'm connecting there and there. The other one also connected there and there, so they're in parallel. Right?
Yeah,
I know, there it is here. I'm dragging that one up. That's, I don't know.
I just, that already makes sense to me, so put it like that. Just,
Okay.
but it's alright.
So those are good. Check mark, check mark. C and D. What do you think? It looks kind of weird. Okay, what would be wrong with C? Let's draw that out. We've got this situation. Is it a hazard?
Not no.
What do we got? Positive to negative, and negative to positive. So we actually don't even have a positive and negative down here. It's a stalemate. No potential difference, 0 volts.
Not for useful.
So it's not a hazard, it's just not useful. So you did good, you didn't blow anything up, but it's not working.
It's a good mistake to make.
Okay, then you got D. So how would I draw D? Draw it the same as this one. I can do that.
You're the one sending. You're a professional. Show an example where it just starts. I send them to you.
What do we got? 120.
How do you know what you're sending? How can we know what's sending? The voltages are opposing each other.
They are. But are they?
Well, I guess not really, but in theory, I guess, yeah.
Okay, let's look at it this way. From this point, if I measure the voltage from this side, without these connections, if I measure the voltage from this side to that side, isn't it still 0 volts? Because I've gone, if I measure here, I've got more negative. If I go positive to negative, and then I go positive to negative that way, let's put the letters in there,
Short circuit.
then I'm actually still measuring 0 volts. Still measuring 0 volts across those 2 points. But here's what I've done. I've caused, by my stupid connections, I've caused circulating currents to exist in both sources, limited only by, if this was batteries, limited only by the internal resistance of those batteries. So what are the internal resistances of these windings?
Small, very small.
It's the resistance, yeah, exactly. So having them go the opposite way, let's see, current is going positive to negative, but the way I've drawn it, I've actually created basically think of it this way. If this wire wasn't there, it would be good, but because I've connected the last connection, I've created a 0 ohm path except for the battery's resistance, and I've caused a short circuit. So that's why it's a short circuit. And if this is happy in itself causing a short circuit, I'm going to get 0 volts potential out of those 2 potential points, here and here, 0 volts. But that's a short circuit. So if the load, and we haven't gotten into this yet, but if the load is drawing, I don't know, short circuit, 8,000 amps, I don't know, whatever it is, 8,000 amps, don't you think if this is drawing current that it's going to take it from the supply as well? Yeah, so if any fusing is going on up here, hopefully those fuses kick, blow open. Mike?
For the short circuit, if you measure from your 2 bottom green points, would that still be, or what would you measure there?
0 volts.
Even though it's part of the short circuit?
Yeah, because you got this. You got these 2. What you're doing is you're measuring the voltage across one and the voltage across the other at the same time.
Oh, okay.
Right? So one voltage in the loop cancels the other one out as far as potential goes, but between themselves, it's a circuit in amongst the 2 sources. So your transformer would start overheating, and it would suck it from the primary as well, and this would be that situation. So what did I write down for there? When primary energized, low wires come effective. Yeah, oh, I see. Yeah, that's what, there's no potential. And then on the other side, they've got those exact examples right there. So you didn't have to really go too far to find them. Okay. With that same transformer we just connected up, guys, we've got 4 possible options. Or 2 possible options? 4. 4 different options. So this page shows you got a ratio of, on 4,800 volts, you can go 20 to 1. You can either go 4,800 to 120 or 4,800 to 240. That's 2 options. So the ratio, the overall ratio would be 20 to 1 for the what one? 4,800 to 240. 4,800 to 120 would be 40 to 1. A 40 to 1 ratio from input voltage to output voltage. Primary voltage to secondary voltage. Right? The next one is the 2 other options. We've got using 2,400 volts instead of 4,800 because that's what our supply gave us. We have 2 other options. We go 10 to 1 or 20 to 1. So 2,400 to 240 is 10 to 1. 2,400 to 120 is 20 to 1. So 4 possible configurations, and so that's why it's so versatile.
So are those the 4 common? Is that what you're talking about?
Just options.
Okay.
Yeah, depending on the installation. But they're all correct. I guess they're showing you the correct ones. 3-wire. really new here, it's just
Connect the same.
kind of adding to, and here we go, three wire
What your
services.
services and what you want on the backside.
Yeah.
Maybe what wiring you have, different amperage.
And we're one stage up here. That's fine, that works. So what we've done here, in a three-wire service, say you're 12240 to your house, and you had 4800 volts out on the line. It's usually higher, but let's say it's 4800. Now I can establish a ground point on that series connection. So if you've made a series connection on your secondary, I could make a three-wire circuit out of this guy by running a neutral. Let's put the neutral down here. And the code says that whenever you have a system conductor that is the neutral point, which is what this is, the neutral point or the center point between the two lines, you have to ground it. Reestablish your ground reference. And usually you do it right at your transformer. Anyone done that? Grounded the transformer? XO point, we call it the XO point. On the transformer, the zero potential point. Yeah, so there's X1, there's X2, there's X3, and then we have XO. It's the neutral point. And so that is your neutral conductor. The neutral only carries the unbalanced load. So if these two are carrying 416.67 amps each, maximum, I would have 0 amps on my neutral, right? But if I have, let's say I had 400 amps and 200 amps, well, now I'd have to carry the remaining 200 amps on the neutral. It would mean that I'm using some 120 volt loads somewhere that have to return through the neutral path. So now you're looking at it from the point of view, we learned about three-wire services. Now you're going to say, well, what's the source to those services? Yeah, I noticed some glitchiness when it comes to people's understanding of three-wire. I don't know what it is about that third wire. There's this stab of neutral in there. I don't know what it is, but it's like people look at it and it's like, forget it. I don't know, especially when the neutral breaks. So be prepared to do a broken neutral connection again. So maybe have a look at that again. We'll try one. Not tomorrow, but for your test. It's three-wire. So we've got a 60 watt load and a 40 kilowatt load. So in this example, 4,800 volts, I think I did a different one here, but 60 kilowatt load and a 40 kilowatt load. It looks good, right? 100 kVA. I just add up the VAs, 60 kVA and 40 kVA, it should be 100 kVA. Why is that bad?
Carrying more load than
Yeah, one winding. So we cannot exceed 50 kVA on each phase or each winding. Right? So that's why I told you guys to go with the winding, because sometimes it looks good. kVA in equals kVA out. Hey, it looks great. How much current would that be on the 4,800 volt supply, 400 kVA? What did we determine? 20.83. So kVA in, I got 100 kVA in, it looks good. Check the secondary. Make sure that it's not unbalanced. I was doing work in it's a coffee shop, and they had a breaker panel that they're saying that we said they were overloaded, right? So they said, well, can you come in and see if you can fix it? So I had to go there during peak operation, when they're using every coffee maker, every grinder, whatever they have running, all the lights, turn all the lights on, and then I'm checking each breaker to see how much load is on each phase, right? So, but there are 3 phases. And I made a note. This is where your detective skills come in, and you make a note of each phase. Breaker 1 is phase A, breaker 3 is phase B, breaker 135, right, is phase C. So you keep writing it down and keep writing it down. You see where the heavy loads are, and you say, okay, clamp line 1, clamp line 2, clamp line 3. So let's just say it was single phase for your example. I had like 60 kilowatts divided by 120 volts. How many amps is that? 60,000 divided by 120.
5.
500 amps? Okay, well, it wasn't that high. It was a 100 amp service. So. Okay, and this one, 40,000 divided by 120.
3.
Okay, how much would the neutral be carrying?
166.
167 amps, roughly? Okay. Phase A is really overloaded, 500 amps. What should each phase be drawing maximum? Yeah, 416. So I want to try to balance out the phases so the secondary on the transformer doesn't overload either winding. So that's what you want to do. You want to always make sure when you're connecting things up, like say you're wiring kitchen receptacles, and you've got a bunch of those 20 amp receptacles, and you're going to run a 2-wire, 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 and you decide to get the little mini tandem breaker. Well, the little mini tandem breaker connects to the same phase. So if they're running everything off the same phase, if you overload one phase in your panel, it would just be a matter of moving some things around so that you don't have that happen, right? So the idea is that you can control where your loads draw from by just the positioning of your breakers. You guys have done that? Have you done some balancing a little bit to circuits?
What,
It's really
is the
important.
whole break, like the whole panel trip then in that case? How's that work?
Well,
What
you
trips?
No,
Nothing trips.
nothing would really trip because,
So like, it's just hard on everything, the equipment? In a house?
actually, in a house, if this was, say this was a 100 amp breaker, let's say these weren't these loads, but whatever, say it's a 100 amp 2-pole, this would be your 1 pole and dot, 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 dot to your other one, right? Well, I guess it would trip because it would be higher than what it's supposed to be.
Okay.
But, you know, what they're saying here is if, and a lot of times this happens where you only have a primary switch and fuse, and the secondary doesn't have to be fused or switched. You have to be careful in that case because your primary is happy, but your secondary is not. So in some situations, you don't have a fusing on the secondary, only on the primary. It's normal mostly to have it only on the primary. We'll learn that in the code. But anyway, the idea is try to make sure you balance out both phases. Don't have one at 80 amps and the other one at 20. You know, like bring them to, well, you wouldn't want 100 anyway. Let's say it's 80 amps maximum on a 100 amp breaker, right? And you're full tilt, running full tilt, you got 50 and 30. You want 40 and 40, right? So you got to take 10 amps off of one and try to get over to the other phase. Now they're happy. So that's kind of what I'm saying. I'm trying to put this in a practical sense rather than just looking at this and saying, I don't understand. A lot of times you're physically working with panels and how to manipulate the loads, right? You are in control. Okay, now we're going to talk about paralleling transformers. By the way, just let me get rid of this. This might make more sense to you if I draw this 3-wire circuit just before we get to paralleling. additive or subtractive?
Be awkward if this section
Okay.
Tasty.
I really love this show.
Tasty.
This is actually
No.
Okay, this is what it says on it. What do I draw for voltages? What do I draw on the secondary windings?
30. No, wait. No. Shut up.
Each one. 120. My tip to you for the day is to write those voltages on each winding. Write everything per winding, like we've done here, to help you to see that you don't exceed the maximum ratings of either voltage or current or VA of each winding. So how do I do the connections on that guy? If I want to have both voltages available, what would I do?
Serious.
Nope.
Serious.
Series, because now I can take
You wanna
neutral.
You wanna get 240?
Line 1. And line 2. So I can have all the voltages available.
How's the lid? Dodge it. Looks good. How about that? More tight. Oh my god, done. Very low. Alright, good. It's not your thing, it's not. It's my shit.
Remember this? So this is all we showed you before. Line 1, neutral, line 2, gave you the currents. There's the supply. So this will actually square the circle, as they say. You're going to see where the currents are coming back out. So let's give it some instantaneous polarities. Which one do you want to be negative? 1 or 2?
2.
2? Okay. So which way does the current go into primary?
Opposite of that.
No, it goes.
Wait, oh, sorry. I thought you were talking about
So we're connecting our supply there
I understand.
from negative to positive in the primary. It's like a small load to the source. Okay, if H1 is positive, then what is X1?
Positive.
So the overall polarity is X4 is negative, X1 is positive, correct? So I'll transfer that over to the final load over here. What voltage is this guy getting?
240.
240, okay, it's negative and positive, so the current goes up
Series.
10 amps, right? And it's 240 volts. Okay. How many VA is that?
30.
2400?
Isn't it? Damn it.
36.
There we go. VA, sorry.
There it is.
Easy. How hard is this?
That was so easy, that math. Wow.
Okay. 30 amps.
I can almost.
What's the voltage?
120.
What's 12 times 3? 12 times 4. this VA, that VA, and that VA. Which way is the polarity? If this is negative here and positive here, what are each one? Each load. What's this one? Where's the negative and where's the positive?
Positive is the one, or, yeah.
That?
Yeah, that one, yeah.
The opposite way you said? Okay.
Yeah, more or less, I guess. Depending on.
Okay, what about this one?
Negative and positive.
This way?
Yeah.
Yes.
Yeah.
How can this point be marked negative and positive at the same time?
Neutral.
It's neutral.
Because it has to have a reference. This is negative with respect to this other point. So it's only negative with respect to that point, and this one's only negative with respect to that point. So this is like two potentials in series that have the same polarity, series aiding, right? Okay, so 120 volt drop plus a 120 volt drop is 240 volt drop. That's really what it is. Okay, so which way does the current go through the load?
From the bottom.
From the bottom to the top, okay. Negative to positive, okay. How much current is the neutral take? 40 amps, 30 amps. So do I have to supply this node with current or take current away from that node? Take it away. Take it away, take it away, take it away, take it away, take it away now, right? You sure?
No.
Yes.
Yeah.
God damn it.
Be confident, Alex.
Testing your confidence level. Okay, so 10 plus 30 is 40. Okay, that's great. Okay, what did this have to supply? Well, this one's 10 amps here, right? And this one's 10 amps. So how much is line 1? If this is 30, 30 up here plus 10 is 40. And this node here, 10 plus 40, 50. Okay, now take it to the transformer. This is where the connection, it's the only reason I'm doing this actually, because this is just review, right? Yeah. This part here, what happens here? Well, this winding is positive to negative, positive to negative. It has to be the same potential as the load. Positives and negatives joined together. However, this is a source and this is a source. The 120 volt source on the secondary being induced from the core by the flux now becomes a source. So the current is actually going this way. How much current is in each winding?
40.
Each winding. How about the bottom? It has to be 50. You already figured it out. How much current here?
40.
40. It doesn't escape. It has to go there. Right? Okay. 40 plus 10. Does 40 plus 10 in this neutral point equal 50? There's your complete picture. Now, did we overload the transformer? Do we have to get a bigger transformer for this?
No.
No?
Well, it's technically still done. You just can't go over your maximum VA.
Okay, 30 kVA. What do I have to do on each winding? What's the maximum kVA of each winding? 15. So this is a maximum of 15 kVA, and this one is a maximum of 15 kVA. So now we're going to go 40 times 120.
Why are we talking about 15?
4,800 VA, we're good. 50 times 120. 6,000, we're good. Good thing. Yeah.
So, but on the primary side, we had 25 kV, oh, it's volt, sorry, I thought it was a VA. My bad, my mistake.
It's all good. What is the ratio of voltage?
A lot.
Well, there's two voltages. We generally think of this as a 240 volt connection because it's in series, and we've grounded the center point. generally think of it as 240, so you go 25,000 divided by 240, I don't know, it's,
0.171 ratio.
0.17?
No, 104.17.
Oh, okay, 104.171, okay. So if you've used 240, is that correct?
No. It's 10. I
No,
got,
I think he's right.
okay.
Yeah.
So 104.
It'd be like 100 for sure. Maybe a little more than 100, yeah. If I used 24 kV, it would be 100 to me, but I didn't use 24. Okay, so what would be the current in the primary winding? How do I figure that out? We know that the transformer is happy because we haven't overloaded each winding. Wouldn't I just add up all the VAs?
Yeah.
Generally, you would. I mean, technically, we learned that you shouldn't add VAs, you should add the components of those VAs. If these were mostly resistive loads, let's call them watts, then we could add them directly. So we're just going to add them. 3,600 plus 2,400, that's 6,000, so 10,800 VA. Is that right?
Mm-hmm.
So I added this one, I added this one, and I added this one.
It's just equals your total VA.
VA in equals VA out.
Yeah.
The VA out was the sum of those three. The VA in, 10,800, divided by 25,000, it's going to be pretty small.
432 milliamps.
What?
No, is that? No, that's
10,800 divided by
432? Yeah.
Wow. You sure?
0.432.
no.
Nice.
Yeah.
Nice. Is that going to cause a lot of line drop?
Not too much, no.
Half an amp? Not really.
99%.
Not my.
Line loss, not much. I squared R even if I square it,
It's not mine.
be 1.6 roughly. I squared that times by the resistance of the wire. Yeah, it's pretty good. So I think I've covered a few things here just by doing this one example. Okay, now paralleling. Any questions by the way?
Yeah, quick question here.
Yeah.
Well, how did you get the 15 kVA for the max on that one?
30 kVA divided by 2.
two.
Because it's a dual winding secondary.
It's
If it was,
Multi-winding.
multi.
if it was
Multi.
in parallel though, Ron, instead of being in series, would each coil have 30 kVA or
15.
even if it's in parallel?
Doesn't matter. As long as it has two windings on either the primary or the
just split it.
secondary, it's half the VA for each winding.
Oh.
Yeah.
So it doesn't fall.
Okay, conditions when paralleling transformers. Okay. I gotta redo this.
There you go.
So generous. So generous.
Don't ever buy a transformer with aluminum windings, by the way.
January.
But Ron, they're cheaper.
They're a lot cheaper. I put one in because it was light and I was by myself, and I could get a rope, hoist this thing up into a upper space, installed it. Got a call the next day that the thing melted. And the fusing was proper, everything was proper. The panel, who knew what kind of load they had? I put a little bit bigger size in, didn't matter. These guys had like an aquarium shop and they had like tons of lights in there and whatever. Maybe it was a grow up too, I have no idea. But anyway, it melted the windings. And we got blamed because we put the transformer, you know.
Right, but why, like,
But
why would it melt, what really made it melt, like, I think?
The aluminum?
Just other than.
It's just it's bad design, I don't know. It's
Like, you didn't melt it that fast overnight.
Why would they even make them if they're that shitty? That makes no sense.
Yeah,
He was just used.
Black market.
I do have a question.
What was the CSA approved?
Black market. No, they can't have black markets. Can't. If they do, they go.
Yeah, ballast lighting takes a lot.
Okay, what paralleling transformers means is it say I want two of these transformers this is one transformer, and I want a second one to run in parallel, like a parallel source. Why would you have two transformers? Let's say I had two 30 kVA transformers, now I can get 60 kVA, right? But I didn't want to buy the big 60 kVA transformer, I actually had better real estate to put in two 30s, right? Or whatever. I did not want to put a big 250 kVA, so I put in two 125 kVA transformers, which is probably more practical. I don't know if you've seen a transformer that's about 125 kVA, but you know they're probably that big, right? So what would a 250 be? Yeah, it's bigger than that. Bigger than that. It's pretty large. Dry type though, right? Because you have to have the airspace cooler. So you got to have. Here's the rules. Same primary and secondary voltages. So I'm going to put two in parallel. I got to have the same voltages. You can't put one that's rated for 600 volts and the other one's 40, right? Something's wrong there. Okay, because what happens if the voltages of two transformers, why does it mention percent impedances at this point? It shouldn't. Each transformer has a limiting factor of impedance. And if they differ in how much impedance each transformer will limit the current by, because it's not an unlimited supply of current, it's limited by how much the transformer can supply and its resistance, its impedance, its reactance inside, right? So it's not 100% connecting to the grid. It's not like you're connecting right into bolting on Hydro's high voltage grid. The transformer does limit the current a little bit, and there's a certain amount of maximum current that will short circuit if you got a short circuit. Huge, huge power though, guys, huge power. Like if you've ever seen anything short circuit on a big scale, or you've YouTubed it or whatever, you know, people die. Like it's a lot of power. And so I'm not going to take this lightly, but if two transformers with different percent impedances, and we'll get to that topic later, if they differ by as little as 2.5%, the circulating current between the two parallel ones on the primary side can get as high as 25% of what your full load current is, which is a lot. And why are these things drawing current when they should be only drawing magnetizing current? So what happens, it's kind of like those two parallel batteries that we did when we did that secondary connection up here a little while ago, showing the circulating current. That's what would be happening in the primaries of these transformers. It would also be happening in the secondaries of the transformers. So you've got to have the same voltage and the same primary and secondary voltage. So here's what would happen if you had two different voltages. You get this circulating current between them. 24 volts in parallel to 22 volts. How does that give? And I did a little bit of math on mine, and you know, I'm not going to sort of bore you with all the math, but you end up with, like, if you have a load, I assumed 4 amps, and you could try this at home if you really want to. I assumed 4 amps. You get roughly 22.5 amps to your load. It sort of shares between the two. But what's going on inside is a lot of drop. There's a lot of voltage drop and a lot of losses. Okay, yeah. Not going to bother. Try the math. Do it like 24. How much current did they say here? 4 amps. Yeah, there it is. Okay, 4 amps. So if you have 4 amps there, what's the drop across the 0.25 ohm resistor? That resistor is the internal impedance of the transformer. Think about it that way. So if you have 0.25 ohms and 4 amps, 4 times 0.25.
1.
1. So you get 1 volt. Okay, positive to negative, negative to positive. The overall net of that is only 23 now. You've dropped it by a volt. Okay, then you got 4 amps flowing through this one, and 22 volts. You've got a 1 volt there. It ends up being, why do I have half of it? Oh, when it's loaded, yeah. But when it's unloaded, you're going to get 1 volt again. 1 volt again. So if you look at it this way, I've got positive to negative. I also have positive to negative. So this would actually be 23 volts. So you would add, I don't know why, when I loaded it I had 22.5, but that's a different example. Unloaded though, this thing is circulating between and the output is only 23 volts. So you've actually dropped your output voltage and you've overheated your transformers unnecessarily. So make sure your voltage is at. What I mean is, you have the same voltage, 24. Okay, so anyway, so they've done this and they've figured out that the difference between that is 23 divided by 0.5 gives you 4 amps circulating between them. Make sure you have the right polarity. So here's what happens if you connect the windings in the wrong polarity. Now you have circulating currents in here. Is this one a short circuit or what is this one? 96 amps. If you work this out, it works out to 96 amps. So it's not a short circuit, it's an unnecessary circuit of huge current. Maybe it's overloading the windings, right? So don't connect them with the wrong polarity. We'll do an example. We'll do a big example here coming up in a second. Okay, and the third thing that you must do, all transformers must have the same percent impedance. Think of this as, you've heard of a battery, your car battery having a certain internal resistance, right? It's the same thing for a transformer. It has a certain impedance inside it. Obviously, it's not going to be 0, right? So it'll have a percentage stamped on it. 2% impedance, 2.5% impedance, 3% impedance. Make sure that each one has the same percent impedance when you parallel them. So what are the 3 rules, because you have to remember this, the 3 rules, for connecting transformers in parallel? Same voltage, primary and secondary, yeah. Not the same VA, no. That's one where it's not, it doesn't have to be the same. You could have a 40 and a 20. Oh, the connected polarity, make sure you connect the polarity properly. Yeah, okay, what else?
Same percent impedance.
Same percent impedance. There you go. Okay, how do we connect to the load? Doesn't matter if they're additive or subtractive either. As long as you connect the ones to the ones and the twos to the twos. Doesn't matter how they're built, as long as you connect them right. Okay? So here's an example. I'll draw this. Sort of a different example, but similar. One transformer, second transformer. These are not the same transformer, these are 2 separate transformers. What are these?
Single pole, double pole, like a disc.
Other way around.
Single pole,
Double.
double pole,
Double
single
pole, single
throw.
They're basically a disconnect switch. So a fusible disconnect switch, I won't draw the fuses, but just understand that when you have a disconnect, you have to disconnect both hots, right? Both ungrounded conductors, so that's why they're double. Okay? Could be three-phase, then you'd have three. I'm not going there. It's complicated enough. When you connect these up, what do we want? Let's do an example from the book that I have here, because for time, I'm just going to get right to the main example. Volts. Let's do a 3-wire. So I guess I have to draw this differently, don't I? Just add a winding to that. So the rating on these, this is a sorry guys. Very good. That's what I meant to do. So I made this one subtractive and this one additive.
Your semis.
Okay, these are 600/1200 to 120/240 volts on each transformer. So how do I make the connections?
First row of
Oh, sorry, I need to give you the voltage of the supply.
Oh, yeah.
Know that, Jeff.
That makes sense?
Yeah.
Okay. So what do I do first with the rating of each winding? What would you do?
label the coils.
Draw it out.
Draw it out. Do you want to try this one? Just connect it up. Draw it out. Did you draw it out? No?
That's what it's.
I just say above 9 acres. Above 9 acres.
What would I label each winding with though? Just so I know.
30,000 kV.
600.
Each winding. Yeah, you would, yeah.
Yeah.
But
30.
what would each winding voltage wise?
600, 600.
600, okay.
Oh, there.
600.
What about these guys? 120, so that'll lead you in the right direction, you do that right away. That's step one. So I don't want to do it for you, the learning will be as you do it. Okay, in this case, it's better. Because they showed you how to connect two dual winding. How about two multi-winding with a 3-wire coming off? It's going to take right there, right there. It's not hard, it's the same principle. So that one, as long as the ones are together, and the twos are together to the same bus. So usually you don't draw them joining the windings, usually you just draw them right to the bus. It just makes it easier to visualize. And this one here, X2, X2, X1, X1.
Well, that's for two of the same.
Yeah. What if they're and added? What about this one?
Same thing.
Ones go to this bus, twos go to this bus, both ones go to this bus, both twos go to that bus. So it's just,
Slightly different.
it's different connections, but look at the ones and twos and you go.
Same thing.
It's like, you can count to 2, or to 4,
I know.
once a leap. You can do that.
Maybe grade 2.
Yes.
You just connect the one that's the same box.
So up there, you just connect the rest.
Oh yeah, so you connect X1 to L1, X4, X4 to L2. I think you have to put a neutral.
Yes. Oh,
So you connect the two middle bits, neutral.
to be serious, if it's there's a neutral.
Doesn't have to be. It's just we have a neutral.
There was other
Yes, I
you didn't answer.
Why would we run a neutral if we didn't need the neutral? You're just running an extra wire for no reason.
The,
Doesn't
the
have
one is,
I don't think.
let the one before.
Oh, no.
No, you just need to connect them through neutral.
So looking at
It
this
never,
one,
it just never showed
let's call that line
a
1.
parallel. So
Each
this is
one, each one, also goes to each 3.
See how-
I know what you mean, the only ones they show us are.
Even numbers in there. So here, 2, 4, 2, 4.
There's nothing, though. But
This one, this is X1, so this should be both odds.
that's series.
So 1 and 3, yes.
Parallel.
That's parallel.
2 and 4, yes.
So you're thinking down.
2 and 4.
No, what if this was parallel?
Yeah, that one works. So that's how
Just
that's
assuming
all I
this
just
was-
look at the numbers.
Maybe.
This one here, 2 and 3 are together, so really you're looking at the 1s and 4s in both situations. 1 goes to the top bus, 1 goes to the top bus, check. Check. 1, 4. So they did this. And I don't know, look at the other ones and see maybe there are more choices, or this is the actual only one that's
I wonder if there's any good videos on this.
2, 4, that's good on primary, secondary.
If you have a three-wire distribution, it might have to be.
That's all I'm doing.
series.
1, 4, yeah, that's it. Okay, so step 1, connect property.
Parallel still needs a neutral,
Okay.
I think. I'm getting confused. Step 1, don't screw this up.
Yeah.
You should be able to do this with the knowledge you get. 3 rules about paralleling. Are they the same voltages?
Yeah.
Check. Check. Yes, they are. They're rated for the same voltages. You have to agree with the KVAs, Clay?
Yeah, sure.
No.
Parallel. Okay, he's on a different role. He's doing something else. Okay. You have to worry about the KVAs when paralleling. It doesn't mention percent impedance, but I'm going to assume that they are the same percent impedance. Okay. We're not going to get to that stage until the next round. Okay, so we'll deal with that next time. But that's one of the conditions, for sure. So it looks good. I threw the switch in there because I'm going to talk about it last. So don't worry about the switch. Just consider this just to be H1 and H4 on each one of those. So how do I connect these guys? Parallel or series? Primary?
You want the end to
No, we're looking at primary. Why?
Hold on. No, it'd be parallel. If you're right. Yeah, it'd be parallel on your end.
Why?
Because if you're connecting both transformers at once, you can just add them all to the series.
Oh, no, you don't. You connect these in parallel with each other. These two are, that's the whole goal. Talking about each transformer. Do you?
I thought that's what you were asking.
Yeah, sorry.
You want 600.
Looking at one of the transformer's primary windings, multi-winding, right? What do you do with the first, what do you do with the two 600-volt coils?
That's in series.
No.
Series.
Series.
Yes.
600 plus 600 equals
1200.
1200. You got to look at what your source is. That's the first situation. And
Oh,
then I
that's
can do-
the series of parallel shutdowns is just based purely on your source.
You cannot exceed the winding voltage. Supply the voltage with a larger. Supply the winding with a larger voltage than is rated for.
Okay.
So 600. If I have 1200, then I have to put them in series so that each only gets 600.
So if it's 600 source, then you have to.
Then it would be in parallel. Yeah, it's all based on what your source is. So that's, I guess, step 2. Draw the voltages, step 1. Step 2, figure out what your supply voltage is and connect the primaries accordingly. This is where I pause. You guys.
You sat on
Okay, how do I connect the primary then?
One bound to L1, the other one to L2.
Okay. The other one is it the same configuration, so make sure you do that. Okay. I'm happy. The switch is off, so I'm really happy. Yeah, don't connect them up if the switch is closed.
My fireman makes fun of me if I don't do it when it's live. Calls me a little girl.
For the 600, that's 600.
So what do I do with what do I do with this one?
You made a mistake,
secondary.
I'm afraid.
I did, I was like, legit, yeah, that's why.
That's my desired output voltage to my loads. So if that's the desired voltage, then how do I connect them?
Is one in series and one in parallel?
This one be in series? Yes, okay. Let's connect this one up first. Where does the neutral go?
Middle.
Right next to the ground.
I'm happy with that.
Yeah, and make sure you reconnect it like
Around?
Michael said.
Yeah.
Good job, Mike.
Thanks.
So why would this one be in parallel then?
What?
Because of the 240?
No.
No.
You're going to produce 12240 from one, and you're going to have another source doing the exact same thing. So whatever you do to this one, do the same to that one. Yeah, they're both in parallel. If you have parallel supplies, parallel sources on your secondaries. What you're doing is you're adding the capacity of another transformer. Let's say this one wasn't big enough. So instead of replacing it with a bigger transformer, I can add another one and put it in parallel. And now it will draw equally from both. Well, not equally, but within their percentages of KVAs. So yes.
When would it be parallel then? Is that a stupid question?
There you go. How's that? Grounding them together.
Oh, I see, that threw me off.
I just looped it through one so that I didn't have to cut it.
Genius, yeah.
Okay. What about line 1?
X1.
X1.
Both of them?
Okay.
Yep.
Pretty easy. It's not hard, right?
Right.
And X4 goes the other one.
Line 2.
Is this what you guys got?
Yeah.
Awesome. You got 100% on the connection. You did that.
Just kind of crazy. That's the really.
Don't forget to ground it.
Give me a transformer, I can do
Let's
it.
get again.
So connect properly. Check. What is the KVA of the whole bank? You guys want to try these answers on your own?
Can you just add them? Hint? Gotcha.
Pretty simple.
Hint, hint. If the secondary wanted 240 volts and you put that in parallel, would you take out the neutral?
It's the joke
How
of the
would you
day.
get 240 out of putting the two in parallel?
I don't know.
Because it's transforming like 5 to 1.
Well, if you wanted 120
Hint.
then.
5 to 1.
120 in parallel? Would you take out the neutral?
120 in parallel is still 120. You put 2 voltages in parallel, it's the same voltage.
Yes.
Parallel voltage is equal, right?
Yeah.
Okay.
Yeah, it's okay.
Are you asking how we get 240 for what we've done here?
No.
Okay.
I'll figure out how to ask it better.
Okay. Think about it. Think about it. It just finish the question and might answer it everything for you. I don't know.
Is it
Like a good way
Okay, what would I do for bank KVA?
Is it 90?
Can you just add them?
You got it.
Yeah. What's the value of that number? Like, can we treat those two transformers down as one transformer and then use the?
It acts as a 90 kVA transformer now.
Okay.
The whole system. The system from this high voltage side to the low voltage side acts as a source to supply that voltage, both of them. So you've just increased the capacity of one transformer by putting another one in parallel.
So you could theoretically put like 40 kV on the right-hand side transformer as long as you're below the 90 of the two together. That'd be okay.
40, oh, your load?
Like,
Your
so
loads can go up to 90 kVA.
Right, doesn't matter what how it's
Yes,
loaded.
that's right. It will automatically take more from the 60 kVA than it will. It'll take 2/3 from the 60 and 1/3 current from the
Yeah.
30. It's amazing.
Yeah, kind of.
Phil tells.
That's why
I think I know what you were asking me.
Yeah.
The 120 states.
What's the voltage ratio?
120 coils. 240 is what?
Well, it depends which one you do. If you do 1200 to 240, then that's the overall voltage ratio. Use the bigger voltage
Then you could just
as your secondary voltage. 120 is just the option
you
of
could just
the
put
center point.
So if we go
120
yeah,
that's here.
1200 divided by 240 then?
You go 1200 divided by 240,
Or you go
divided
600
120.
by
We're talking about it right now.
5 to 1. Each windings ratio is different. This would be 5 to 1, 5 to 1. These are in series, yeah.
Cool though.
Maybe another stupid question. Is the secondary always in series?
Not always, but in this case, for three-wire circuit, yes.
From
Three-wire it has to be. And your series connection is your center point for your neutral.
That answers my question.
Okay.
Your first one?
If the neutral didn't exist, I would have a 240 volt. If I didn't run this third wire or this wire here, just had line 1, line 2, it would be 240 volts only. You have no option, right? Yeah. It would still run the same. You wouldn't know the difference.
That's what I was talking about with the extra neutral.
Okay, so they let you finish that one?
No.
I'm gonna let you finish.
That's it,
Okay. Yeah, because I want you to practice. In the end of the lesson here, it says closure voltage. Possibly. Testing the closure voltage before making the final secondary connection. Okay, so I'm paralleling two. Before I put this wire in where the voltmeter is, what voltage should I measure there, Jeff, before I put that wire in?
120.
It's funny, it says 0 volts right there. So if you measure 120, then you're going to get a short circuit. So what you do is before you connect the loads and you've energized the primary, you do a closure voltage test. It's called the closure voltage test, and you should read 0. There should be 0 potential difference. If this is producing, let's say, 120 volts, negative to positive, and this is also in parallel, producing negative to positive 120 volts, then these 2 points should have the same potential. So you should be able to, if this one's connected, this should have no difference. The two sources should actually produce the same potential voltage, because that's why you're paralleling them. Before you connect them, you want to determine, you want to make sure that it's 0.
Because the line is already getting 120 from X2, it should be the same.
So here's what you're actually doing. You don't connect this that way, but you're actually measuring. I like it better if they put voltmeter arrows on this, because then it looks better that you're actually testing X2 to X2. X2 to you're measuring from this point, where my cursor is, up to the other X2. That's what you're measuring. And you should make
Oh,
0.
before. Okay. Is that,
What happens if you don't? What are you going to read, Jeff?
120.
No?
oh,
240.
Good, one job. You know, I don't know, it's like, maybe because it was 128, I'm going to put in the next class presentation that it's 130, you know, because that, everyone gets all antsy when they get close to 130 or whatever.
145.
Anyway,
feel
why
like
is that the case? Well, if you analyze it, you're actually measuring, if you've gone 1 to 2, and then this one you're actually going 2 to 1. So if the 2s and 1s are joined together, that's a bad thing. So you know you've got your secondaries flipped. So before you do the final connection, don't short circuit it with, this would be a short circuit. If you connected this and then turn the switch on, it'd be a short circuit. So that's what we have. Another thing in the code, Dustin, before you go,
It's so fast. 130.
before you go, what happens if because I got 2 switches here. What happens if one of them is open? Is it safe to work on this transformer up here?
No.
Because I've on the primary though?
No.
I think that's
Secondary.
It backfeeds this 480 volts,
It goes back.
backfeeds and produces 12,000 volts on the secondary of your switch.
Better work our line.
So you have to disconnect both of them. The problem is, why don't we just connect one switch to both of them? The code says you can't. You have to have an individual switch to each
But should
transformer.
they interlock then if you have 2 switches like that?
No, you just have to determine that all energy sources are disconnected. It's part of our ensuring that we check it.
How do we keep our
Okay,
job?
there you go.
Yeah.
Now you can adjust it.
Mike,
Yeah.
you want to stay on?
Go.
No.
No.